Perfect. Wonderful. Okay. So I'm really pleased to introduce Angjoo Kanazawa. She is an assistant professor at UC Berkeley, doing a lot of really interesting work at the intersection of computer vision and machine learning. So without further ado.
You're muted.
Hello. Okay, great. All good. Okay, thank you for inviting me. I'm wondering what is it like in person? There's a lot of people.
Yeah, wait, let me try to rotate this without disconnecting all the cables. Oh God.
Oh, right. Oh, exciting. Oh, okay, great. Hi, nice to meet you. Nice to meet everyone. I am so sad I can't be there in person. In-person conferences are awesome. I'm very happy that you're doing that. Okay, so if you're on Zoom, thank you. It's great to see people's faces, Okay, so thank you for inviting me. I know this is a robotics conference, but this is on neural geometry. And today I will like to talk about like our interpretation or journey of like with Nerf, and like the way we're thinking about it, then hopefully how it can give you more insight about these tools. And so I guess the direction that we're really coming for is that of, actually this is a reconstruction of myself from a single image. And this was a PyFu, which was published in ICCB 2019, which in 3 years ago, it kind of already feels like forever in this time of thing. But, this is one of the early implicit representations, and they're also very easy to, train. But anyway, okay, so there's many angles to think about this, and I'm essentially a vision person. And I'm really excited about this idea of capturing reality, which we've been doing ever since we've been around. So this is 45,000 years ago, we were drawing the pigs that we were hunting. And over these 45,000 years, we got much better at drawing, and now we can render all these, we figured out how to render things by hand, including the lighting effects. And then we developed the photographs, and then we developed the film. And so in this direction, these are the current existing medium that we use to capture our reality. But of course, as we know, the world is 3D. And so how can we really recover that missing axis in these representations? And this is something that people have been working on for a very long time, known as structure for motion, or SLAM in in the robot world. And so these approaches can do reasonable approaches, reconstructions in these big cities, which has been used in this kind of commercial applications, as we see in our Google Photos. But I feel like what is next? And so what's next? What's the next medium for reality capture? And I think that's where I'm really coming at. And I think the really exciting goal would be to do casual photorealistic 4D memory reconstruction. And so if you haven't seen this is a really short film reel made all in Unreal Engine by artists who went to Australia and captured all of these pieces by photogrammetry and then put it all together in Unreal Engine. And so right now, if you're a specialist in VFX, maybe you can do this, but you can do this in every day or casually. And I think this is really a necessity, and it's 4D because the world is dynamic and you also want to capture this. So this is like the really, really big goal. Hopefully you can see how that would be useful also for in the robotics context. In this context, I want to touch on like how is all of these developments very different, somewhat different from structure for motion, which we've been doing for a very long time. Well, first of all, you might know that structure in motion is a problem that recovers camera, and a lot of these Nerf type approaches assume that you have camera motion, although you are also solving for this. But I think the biggest difference is that there's used to be a lot more emphasis on geometry. Now there's a lot more emphasis on photorealism. This is an interesting audience because you probably only care about the geometry. But the point is that if you look at it from multiple views, and if it looks good enough, the geometry has to also be good enough. And there's kind of some encouraging directions that point to this, for example, for like transparent objects. Another thing is from partial capture to immersive capture. Previous approaches really wanted to get good geometry, so could only give you 3D on certain things. This one allows you to be immersive. I guess this is a more graphics kind of goal. But the last thing that robotics people will definitely care about is the fact that the world is not static, and you want to be able to interact with it or capture things that are dynamic or deformable. And so I think these will be the directions that my group and I are really excited about. And of course, you can do this. If you can do this, it's great for content generation for virtual world. So this is a video game called Ghost of Tsushima. It's very, very beautiful. And I think another really exciting application would be digital conservation of nature, or just digital conservation of the state of the world as it is today. In particular for forest, if we can capture these things, we can do a lot of vertical analysis, which is very important for, wildfire prevention and such. I also think there's a really cool direction in immersive news or storytelling. New York Times has been doing this really cool thing where they fly drones at these sites to tell a story. This would be a really powerful tool. And then maybe, drones could be doing this. I mean, actually, this is an actual drone flight. But of course, the things that are interesting to this particular audience is to use these ability to perceive the underlying 3D world to interact with it. On the right, we have this motion planning work. This is this nice work from Janet's lab. And then this is another work from Ken Goldberg's lab that is using Nerf to perceive transparent objects, which was not possible. So this is the input image. This is the traditional sensor. And if you do Nerf, you can get these better depth maps that you can use to interact with these transparent things. I think there's a lot of exciting work coming in this direction from Yenchen and Phil's lab and ICRA and all these things. So why are we talking about all of these things? We're talking about all of these things because there's this approach called Nerf that came out 2 years ago, which can give us really beautiful representations. And by this point, you must maybe know, but I will still go and cover the 3 components of Nerf because I'm going to discuss it. And the goal for today's talk is to maybe give more insights as to how you think about these neural representations or radiance fields. So first of all, Nerf has a neural scene representation, which basically models a fog. Okay, and it is optimized from set of input images, like 100 images of the scene. The way this is being done is you shoot a pixel and this gives you a ray. And on every single ray, you're going to ask what is the color and the density of this like fog-like model. And then you integrate it using this volumetric rendering formula, which is differentiable. And then you optimize this by analysis by synthesis or render and compare, which means, give me the thing that explain to me the thing that I see. And this is really the optimization approach. I am breaking it down into these 3 components because the question is, which one of these 3 components is the most important thing in making these beautiful and nice results? You can think about this and maybe we will come back to it. Okay, so Nerf is great and everything, but there is a lot of practical challenge. So for one, this is rapidly changing to, in today's landscape, but original Nerf took a day on GPU to train. And in order to render it, it took 30 seconds per frame, which is really prohibitive for any real-time applications. And so today I'm going to talk about the works that my lab has been doing, which focuses on this, these 2 aspects. One is real-time rendering and one is fast optimization without MLPs. But before I start talking about this, okay, these are the statistics, but before I start talking about this, I think it's really important to understand, like, what is the problem that Nerf is solving? Okay, and in order to have that conversation, we have to talk about planoptic function, which is a wonderful thought experiment done by Adelson and Bergen in 1991. And it was a conceptual device to answer this fantastic question of what is the set of all things that we can ever see? It's very, very nice, cool question. So how can you actually parameterize everything that we can ever see at any moment in time, all the visual reality? And so in order to do this, you can let's just simplify this and let's think about a color snapshot. So you have an image picture. Okay, a picture can be parameterized by a person. So this is a function. The function returns the intensity of light seen at particular viewpoint at the center, and then the view direction by this spherical coordinates. It's seen from a single viewpoint at a single time as a function of wavelength. So these people are really fancy, and so they were saying, what is the value intensity of this wavelength? So this could have even modeled like microwaves and all of these things. But okay, but you see that an image would be formed by sampling all of these different spherical coordinates around me, and that would form an image. Okay. Simply to make it into a movie, you just add a time dimension. This will capture the intensity of light from a single viewpoint over time as a function of wavelength. And so this can capture a movie theater fixed screen over time. But we want to move around because the world is 3D. And so in order to do that, all you do is kind of repeat this type of visualization of these centers where you can actually see different things by these spheres and add the location. Okay, so intensity of light seen from any viewpoint over time as a function of wavelength and any viewpoint via XYZ and any view direction. Okay, so this is a 7-dimensional function with this two for view direction, 1 for wavelength, 1 for time, and 1 for location. And the nice thing about this is that this particular function has no idea of the geometry of the world or where the lighting is from or how specular is this material, has no idea, but it can still reconstruct every possible view at any moment from every position, basically the entirety of our visual reality. And so this is a really cool concept of like, if you can capture this, planoptic function, or like, people call this also light field, or an approximation of planoptic function as light field. You can render all of these cool effects in graphics, okay? But, let's just kind of remove away some of the things. So let's just abstract away the time, focus on a single time for the moment. Let's get rid of the wavelength because we really care about the RGB. Then we are left with this 5-dimensional function that takes in a viewpoint and a location. And so this must look a little bit familiar to you because this is the function that Nerf is modeling. There's a small step in order to get to this because this is a full image. So you have to really integrate everything using the density model to get this particular intensity. But really, this is the problem that is being solved by Nerf. And so Nerf is a representation and a method to approximate this. And if you think about it like this, then it's, we are simply introducing, all of us are introducing 2 representation for the same task. Or we introduced 2 representations. One is called planartree and planoxels, and these stand for planoptic octree and planoptic voxel element, like pixel is a pixel element. And so this is planoptic basically means like all view dependence, basically, or it looks different from different views. And these are basically generalization of one to the other. And I'm going to describe this. And this is the explicit representation that we're introducing that makes things much faster. But that also helps you really understand what's going on underneath. All right. Okay. So this is the planoctree that made it into real-time rendering. As you can see in here, and you can convert this to your existing Nerf to this format, which is a really nice thing for debugging. And it also has these kind of, interactive UI that you can change and look at these things. This also has a WebGL demo that I could go and do, but I think maybe if I have time, maybe I can do it later. But okay, so why is Nerf really slow? The reason why Nerf is really slow is because you have to have lots and lots of network calls. And so like you shoot for every single pixel, you shoot array, and every single time you're like, what is the value? What is the value? What is the value? What is the value? This is very slow, first of all, this dense thing. So you can, if you had SDF or something, you can maybe skip it. But still, this is a lot of network calls. Okay. And in any practical computer science applications, to make slow things fast is to do caching, okay? But caching is hard because you have to sample densely in R5, and R5 is a lot to cache, okay? If we recall this intuition of the planoptic function, we can visually see that the location and the view direction can be factorized. It's not an actual R5 space, but it's like for every single location, you have all of these view dependent effects that you want to capture. Okay. Another way of thinking about it is that like every single point in the world has its own image inside that captures this view dependence. Like an environment map and every single dense thing. But this is also as obvious apparent to the way the original Nerf authors designed their network. As you know, it takes in XYZ, or you might know the network architecture looks like this. It takes an XYZ, outputs the density, and then gets the view direction. So this structure is also already there, but this is an intuitive explanation of why that is so. So if this is the case, then the thing that you can do is you take a slow Nerf network and bake it into a representation that captures this view dependence in a grid. And this is basically how all of these fast approaches are done. So So let's talk about factoring out the view dependent effect first. And so for this, we basically model this particular function, which is a spherical function. So this thing takes in a view direction and outputs color values. This view direction is a function on a sphere. And so basically we use an explicit spherical function called spherical harmonics, which is like Fourier series on a sphere. And you can use this to approximate any function to a degree. And so instead of that Nerf that has this new network components for view direction, we output the spherical harmonic coefficients. And these coefficients, if there are like say degree 2 and there's like 9 bases for spherical harmonics, then there's going to be 9 coefficients for every single channel. And so for RGB, there's 27 numbers, and you have all these 20 or 9 numbers, and you multiply it with these bases, and that will give you a function that you can query from any viewpoint and give you some particular response. Okay, and so this way we can just store the spherical coefficients at these voxel locations, and then now that we are explicitly caching the space, you can do these tricks of only storing the non-empty voxels, which allow you to skip through all of these empty spaces. A little bit like spherical render, sphere tracing in SDF that allows you to skip, and then you can render the things fast. So this is fast because you don't have to do this dense. It's fast because you also don't have a network to query for view dependence. Okay, but with any kind of fast approach, there's a trade-off between the quality and the storage, or there's some kind of a trade-off. And in this particular model, we're paying it by storage. Because it's fast, you have to store all of these things. This is pretty common and still, there's a new paper that is called TensorRF that is kind of going around this direction by, different representation of the space. But, anyway, that's the trade-off. And this is 3,000 times fast. It can be 3,000 times faster than Nerf. Because the storage is incurred, you want to make sure that the world is sparse as much as possible. And so funny thing is that because there's no view from the bottom for this hot dog, if you don't have a sparsity loss, it gives you like a white table, and you don't want to store all of these things. So you add a sparsity loss that makes everything light. And so here are a couple of results. And you can do all of these things. Here's a comparison of the planartree to Nerf, and this is probably not the best quality to look at this on this internet. You can look on the video. But another nice thing, this might be interesting for the robotics folks, is that you can convert a normal Nerf into this planartree format by projecting it onto these spherical harmonic functions. If if you want to use your custom basis, you can also do this. Simply just solve a linear, least squares to approximate the coefficients that requires to model your view dependent functions. Okay, and so this way you can, Alex, the first author, implemented this nice tool called Nerf Viz, which allows you to visualize Nerf in real time. And slowness of Nerf is a real problem because you really need to see what is in there. And especially because Nerf kind of gives you all these crap on the places that you've never seen. So this one, we were reconstructing a room, but in order to see whether it's done properly or not, you really want to slice in all of these things. So this is really handy and like a really necessity thing to do your research. Anyway, there's a lot of concurrent works that is also studying this problem that hopefully you can check it out. But to get to the other part, which is that we realize that once you make it into a planartree, every single planartree has spherical coefficients and density, and you can actually just directly optimize the content of that density in the spherical harmonics once it's in planartree format, because there's nothing different. It's still differentiable. And then if you do that, you can get a little bit better results. And this is why we realize that you can actually just train Nerf for the first 3 hours and then bake in the planartree structure and then optimize it again for 1 hour and then get the same performance as a 16-hour Nerf. Okay. So this really got us thinking, do we really need the neural network to begin with? Because most of the optimization is being done in the explicit space, but we needed it in this work because we needed to figure out the planartree octree structure, and that is not very differentiable. But I have this wonderful colleague who believes in this, and I was like, you have to be able to do this without neural networks. You know, this was our guiding force, and our students really tried many different things to make this work. And then we basically figured out how to do it without neural networks. And so here I'm going to show you a video that's gonna play comparing the optimization time of planoxyls and Nerf aligned to real time. Okay, let's go. This video always has a problem whenever I want it to play. Okay, I fixed it. I did it yesterday and it worked. Oh my God, it's so annoying. Anyway, so, okay, this is good. I'm just going by slowly. So already in 2 seconds, you see this structure coming up for planoxyls. And then this gets better and better. And then the consideration actually for robotics, I was thinking, is that, you know, Nerf is 16 hours of training, but like actually it gets to reasonable, you know, this is still taking a while, but like, you know, after 30 minutes, it's pretty reasonable. And then in planoxyls, you can see after like, I don't know, like 10 seconds, it looks pretty okay. Okay, and then this gets trained for another 10 minutes to get to this, you know, reasonable for graphics people who want really pretty pictures, this you know, metric called PSNR, and we really optimize this PSNR, and therefore you have to train this for 8 minutes. Okay, but for robotics people, you know, I mean, maybe the structure is already enough after the first 10 seconds. It's something really to think about, to take the, you know, take these length with a grain of salt, because they're to optimize PSNR. Anyway, we tried to, you know, to convince that this is not just for synthetic stuff. We did it on real scenes and 360 scenes. And the method is really simple. So you already know the planartree, and what we do is basically we just put it in a sparse voxel where every single corner of this voxel stores a spherical harmonics, and it does this interpolation. So that interpolation was also key and missing in the previous work. And so how you train this is you have a training image, you shoot array, you have this sparse voxel grid, you have this trilinear interpolation. And then you aggregate all of these values and you render a color, and you do this optimization to reconstruct the views. And we also use sometimes you need to, well, we also use this regularization to make sure that the underlying representation is smooth, because this is an inverse problem. And we do this TV regularization, which makes sure that the density and the coefficients are smooth. It's really necessary for forward-facing scenes where there's not that many views. I think in robotics is also, if you don't have many views, you really probably want to do this regularization. And NLP doesn't have to do this because it's a very compact representation. It's a very good interpolator. That's another thing that we found, that it's very important that you do interpolation, trilinear interpolation in this work, because the A allows you to get to higher resolution, and B, it allows the gradients to flow quickly across the whole volume. And you can basically kind of think of the trilinear interpolation as yet another kernel. And so neural network NLPs are also this type of kernel. You know, there's also another interesting insights on the volumetric rendering function. And so there's two types. There's neural volumes before Nerf, which is also very similar, but they had a very subtle difference. The absolute transmittance, difference in the way they implemented transmittance. And transmittance is basically how much does a light reach to me, and then this is the thing that is being integrated before you compute with my own density and color for every single point. But anyway, this subtle difference does make a difference for PSNR. It's an interesting thing to kind of look at. This volumetric rendering function is not like it's still an approximation, so there might be a better form of it. It's kind of what I want to say. We also do this coarse defined structure so that we can get to 512 cubed. Here are some results of the planoxyls, which looks, which can obtain similar or better quality to Nerf. Oh, but then, yeah, okay. And we've demonstrated this on real forward-facing scenes also. We've also done this in 360 parametrization, where the background is basically yet another sphere, like concentric spheres, MSIs, to model the background. The center is done by this voxel, And the background, I think it's a Zoom issue because I just did this presentation yesterday and it played. But you can get rid of the foreground because the foreground is the voxels and the background is being done by this MSI, which is also a planoxel. It's just a reparameterization of the uniform grid to a spherical grid. Okay. But I know that this is done at 12, so I have a takeaway, which is that, yes, we tried Nerf without neural networks, which results in much faster training. It also shows that the volumetric rendering is the key ingredient in Nerf, not necessarily the neural network. These neural view synthesis tasks also require no learning. Okay, MLP is an effective interpolator, but it does not do any extrapolation or magical prior thing beyond interpolation. You can really see that these approaches have hundreds of views, and you want to interpolate it. That's what it's doing. There's no more reusing previous nothing magical about using MLP that brings in this thing. It just needed to have a good kernel. Does this mean we'll never use MLP again? No, not exactly. Opinions differ. I think the flexibility of MLP is still nice and necessary because sometimes you really need to explain away certain things. It makes it nice. I think there's like a nice, spectrum of this thing. You can learn custom spherical basis also. And so there's very, if you put these recent works in this line, Nerf is extremely implicit. Our work is extremely explicit, and it's kind of like a proof of concept. dvgo is something nice in between, where the spherical harmonic spaces are replaced with a learned basis. Instant NGP also has an interesting hierarchical hashed-based representation that has this that represents the volume. I do want to say it's really interesting because this power of analysis by synthesis, the particular way you optimize things with gradients. We could have done this 20 years ago. Of course, compute would have been hard, but I think people 20 years ago were very smart and very, smart about their compute. So I think this could have been done, but it's just interesting that we're really coming back to this. So this is an older work that was doing something similar, but the way they optimized it was take a voxel, project it into two images. If they look the same, keep it. If they don't, throw it away. And so there was this carving approach. This is a different way of optimizing this thing, and then it just doesn't work as well. Although it looks pretty good actually, but it's really the power of analysis by synthesis to get this nice thing along with these new representations. To end with, I think the speed for these robotics or interaction directions, I think the speed is really getting there, but the dynamic scene is still very challenging. The fast training is one way. If you can train really fast in a second, then every single time, if you have multi-view rig for your robots, you can kind of reconstruct it every single time. But then you still want to do the correspondences. You still probably want to maintain correspondences. So this requires 3D tracking and something smarter than that. And existing dynamic Nerf approaches are still, for these graphics tasks and not necessarily for really large baseline tasks and good geometry, I think. Few shot is also really interesting. How can you do this with less number of images? We tried this in Pixel Nerf, but I think what is really missing is to reuse previous experiences. Although, Pixel Nerf is one way, and we designed this in a way that it's not category specific, but I think there's a lot more to go and explore in this direction. And then I think lastly, I think there's a need for easy to modify coherent Nerf toolbox that kind of implements all of these different approaches that people are doing it. And this is maybe something that we're working on. So hopefully that could be something that people want. And I'd be happy to get some thoughts if there's any questions. And thank you. Thank you. I thank my collaborators.
Yeah, thank you so much, Angjoo, for your really interesting and fun talk. And yeah, if there are any questions from the audience, please step to the microphone so that the rest of the room can hear, and then I can funnel it into the Zoom. And of course, if there are any questions from Zoom, please feel free to raise your hand and we
So I have a question, which is, you said, I think in a lot of robotics applications, like you said, we might just want geometry and not, although I think semantics are often important. But is there anything you can do to speed this up faster? Right? If we don't care about colors, so part of the shortcoming of the analysis, which is synthesizing images, we have to have color, and we can't just say have white clouds. So if we don't care about color and we just want structure, what could we do to make it come?
Okay, yes. So
Did you hear it well, Angjoo?
I guess the question is, if you said we only care about, as you said, we only care about geometry. Like if we don't care about the color, can this be made faster?
Yes.
Yes, okay. And so I think that's kind of what I was saying. It's like you cannot, well, I don't think you can separate this away from pictures and color, because I think the goal is to learn from images, and images have color. And if you don't want to have any supervision or rely on like depth sensors, which don't work on all of these things, you need to really use the pixels. So pixels is not a bad thing, but I think optimizing extremely long time for beautiful pixels is not something that is necessary. So this is why I really want you to look at this particular optimization video and feel that like, oh, maybe, you still see some, stuff around here, but, by 25 seconds, maybe this is good enough geometry for you. I think that is what it means to not really care about the color. You still use it, but you don't optimize it for 16 hours to get the highest PSNR you can ever get.
Thanks.
Thanks. More questions?
Hi, great talk. I have two questions. First of all, what are your thoughts on object-centric representations? Second, what do you think about generalizability of this information?
What was the first question?
So the first one was, what do you think about object-centric representation? And the second on generalizability.
I see. So when we did pixel Nerf, object-centric, there's nothing wrong with object-centric representation. I've done them, my entire research career. It's okay if you know that that is the category that you want to reconstruct. And so in particular sense, it's fine. And that's a really nice way to incorporate your prior experiences. You will learn that, all mugs, have this particular shape. And if you're going to do that, why wouldn't you do it in this particular centric representation? I think that's okay. But then that also requires you to know the category and then also predict the camera. I think it's just a case-by-case basis. I'm definitely not against it, but if you want to just take an image and reconstruct it of a scene, it's very hard. I think their scenes and objects are very different. There is no canonical representation for a scene. Like if you have these two chairs, it's not even clear how to canonically align them. How do you pick the first chair? What's the origin here in between two chairs? Like it's not going to be a very meaningful space. And so I think it is really important that if you want to do, like if you want to manipulate objects, sure, assume some objects are known, use some recognition stuff. But what if you're in an arbitrary environment? You still might want to perceive their 3D things. And in those cases, object-based is not the best because they're not objects and scenes. And then the second question was about generalizability. And I think for that, pixel Nerf was one way of doing this, which is to condition the Nerf representation on, condition the Nerf representation on, I guess I don't have any, but condition the Nerf representation on like pixel features. But it simply, what it simply does is like, it just embeds another direction here, a feature of the image. I think it's a reasonable way. It's the way we've been doing throughout the vision people. Actually, it was very much inspired by this paper because the results for this PyFu, because that's what it was doing and per pixel. And this required 3D supervision and pixel Nerf doesn't because it only uses images. But I think what is really missing is like more general 3D priors. I don't think so many things in the world are things in the world are really like empty or sharp edges, I think there are really basic building blocks of like Lego, words that we can learn about the scene. And I think if we can reconstruct the, scenes in that particular representation, this is what I mean by reusing previous experiences, by learning these reusable small priors that is independent of objects. I think that would be a nice direction.
Great, thank you.
Thank you so much, Angjoo. Let's give Angjoo another round of applause before we go to the next question.